Let's do this. The daily today, I think. I skipped yesterday, so it was hard. Maybe I'll come back to it tomorrow, but let's try this. I think it's a graph problem. Hash table, DFS, BFS. So yeah, we'll try it. I don't know if I can solve it, but we'll see. You're given an integer C representing C power stations with each with a unique identifier, ID from 1 to C. Okay. These stations are interconnected via a bidirectional cables represented by 2D array connections. Each element is a connection from UI. VI indicates a connection between U and UI and station. Stations that are directly connected. Initially, all stations are online, given a 2D array queries where each query is one of the following two types. One, X, a maintenance check is requested for station X. If station X is online, it resolves the check by itself. All then check is resolved by operation with the smallest ID in the same power grid as X. If no operational station exists in the grid, return -1. Okay, station X goes offline, becomes non-operation. Okay. Return an array of integers representing the result of each query type from 1x in the order they appear. Oh my god, okay. So we're given 5, all the connections, and then the queries. So initially, all stations 1, 2, 3, 4, 5 are online. Query 1, 3, station 3 is online. So the maintenance is resolved by 3. Okay, so all the ones, what is the result? Okay. So the main is just, then we have 2 to 1, so station 1 goes offline. Oh, okay. The remaining stations are 2, 3, 4, 5. Okay. Now, 1 to 1, station 1 is offline. So the check is resolved by the operational station with the smallest ID among which is station 2. Okay. So you return, okay. Okay. Then query 2. That one just says that query 2, that just says that 2 is not that, and then so the result is 3, which is station 3. Oh, okay. I think a heap is definitely useful. Okay. I feel like it was like a graph problem, but it doesn't feel like it though. It feels like a heap problem. Let me look into an ordered set Python. I feel like that's going to be very useful here. Okay. Basically, what is the purpose of the connections? Oh. I'm kind of confused on the purpose of the thing here. Like, what is the purpose of connections? There's a 2D array connections where each element indicates a connection from U to V. Form a power grid. Okay. Initially, all stations are online. You're given. Oh wait, hold on. Okay, if I say this is offline, that means I'm kind of confused. You're given an integer C representing C power stations with each unique identifier. These stations are interconnected via n bidirectional cables represented by 2D array connections where each represent the result of each query type of 1 to this, right? Oh. Oh, I see. I see that. Okay. Okay. I get it now. This connection is just, it's like this, 1, 2, 2, 3, 3, 4, 4, 5. But, okay, so we can definitely do a map. Right? We could do like a for every we'll do UV in connections. Graph of UV. Can I go to multiple? Okay. I need to think about something. Okay, so can it go to multiple stations? These stations are interconnected via bidirectional cable representing a two-way connection where each element of I is a connection between U to V. Stations that are directly interconnected form a power grid, right? Okay, we could say power grids, right? And there's only one. There could be multiple. let's call this, I got station node class here. All right. Station number and that's fine. So station number, then self dot neighbor. Let's call this none for now. I want to use an array. I want to say array. Just in case. Okay. So first I'm going to do this. So for every UV in connections, for every UV in station, so node, let's call this U, so node U, node V, connections, node U, node V. Okay, so this is going to be station node U, and we need to set node U dot neighbors dot append right? So we have that. I guess root. We'll call it station. Station node 0. Okay, fuck this shit. I don't know why I'm doing this. Let's just do it the typical way. This just makes things complicated. Graph default dict list graph of U append V U V. Okay, let me just print this real quick. Okay, so 1 2 1 3. Oh, 2 goes to 3 as well. Yeah, that makes sense. 3 can go to 2 and 4. 4 can go to 3 and 5, and 5 can only go to 4. Okay, yeah, easy. Okay, so we have a power grid. Then what? queries. So for every OP as state and station in queries, if state equals 1, if state equals 2, pass to pass for every state and station ID queries. Okay, now this is where we have to alter the graph. So graph here, so if I perform the queries, will the resulting resulting graph give me what I need? Maybe. So okay, I guess we can get the res here. So if state equals 1, then so if station ID is reachable, oh my god, I have to delete all the instances of station ID because it's not reachable anymore. Okay, so we'll do this. So for every station ID, for every station in ID, okay. What am I doing? I basically have to so first, okay, this is the easy part. So if station ID in graph, then we're good. Then res.append station ID. If it's not, what do we do here? Check the resolved else. So this means offline. If the station is offline, the check is resolved by the operation with the smallest ID in the same power grid of X. Okay. Now I need to traverse it. Oh my god. Okay, I see. Okay, the same power grid as X. Okay, I got it now. Okay, I see the same power grid as X. Okay, so that's why I need the C. Okay, so basically, how do I know? Okay, I got an idea. Operations. Print C, and then no, print operations. 1, 2, 3, 4, 5. Yes, that's all we need. Okay, perfect. I see exactly what I need to do. Okay, so basically if state is 1, just check if, okay, so if operations of station ID -1, then res.append station ID Basically, this is the easy part. We just say operations of station ID -1 equals true or false. Okay. If it's not, then I need to traverse the graph. Traverse graph and find the smallest. Okay. Smallest is I don't know. Okay, yeah. We're gonna assume that the station ID is the smallest. And then for... Ooh, not the... No. We don't want that. We need to traverse... Well, source is going to be the station ID. But we need to find the smallest, which is... smallest is float in some arbitrary release big value. Okay, so cur is graph of source. How do I go through the graph? Okay, so this is the BFS here. While Q was the Q here. So while Q first poly source n equals length of Q. Nope, we'll do this. Length of Q. Then cur is Q dot pop left. Cur equals Q dot pop left. Okay. For every neighbor in cur dot graph of cur, ID in station SID Q dot append n if smallest, if cur smallest equals cur, then smallest, and then res dot append smallest. Damn it. Okay, hold on. We'll do this. Is the... what is it? Okay, first and needs to be and smallest and smallest. Okay, hold on. And operations of cur -1 and that. Then we set it, right? I guess if smallest equals float inf, then res.append -1. Else res.append smallest. Maybe a heap would have been better to keep track of the smallest, but this is what I can think of so far. And then return res. Okay, that was a lot of code. Okay. So what I'm doing here is building the graph. I'm also building a state where if they're operational or not. Then I make a bidirectional graph. Then I have the resulting operations. All right. Now we have the state and the station ID from the queries. If it's a state 1, then if it's state 1, then that is a scenario where a maintenance check is required for X. So if the station ID is operational, right, then we just add that station ID. Otherwise, if it's false, then we'll start at that source and then smallest, and we'll do like a little quick BFS. So we'll start at this source, do a BFS, q.pop left, then check if our current one is smaller and you are operational. If it is, then set that and then keep going. Eventually, if we don't find anybody that's operational, then we'll just do res.append. Otherwise, we append the smallest and done. It looks good to me. I probably didn't get this though. Okay, we got a infinite while loop. That sucks. Why? Oh, maybe because... Oh my god, I know why. It's because they're bidirectional, so... Okay, maybe do a freaking scene, I guess. Scene. Source, of course. Scene.add. Occur. Because we already... and not... Okay, hold, we could do this. If cur in scene, continue. No point of re-adding them. Okay. All right, come on, give it to me. All right, that looks really good. It might be too slow though. Oh shoot, that looks pretty. Yeah, I got Tilly. Yeah, I got Tilly. I need to optimize this. Let me try to see if I can optimize it. So maybe I can optimize it quickly by... Okay. should we use a heap? How would the heap improve the performance? It's too slow, bro. How can I improve it? Okay, what is the... Give me a hint, bro. Use DFS to assign each station or to assign a station a component ID. For each component, maintain a sorted set of IDs of, yep. We're going to remove the set of components. For a query of X, if otherwise. Okay. I need to... I think this is like a union find thing. It's like I have to like, they're like groups of clusters, and then I have to assign them like unique IDs. Yeah, I freaking knew it. Fuck, man. Plus priority queue. I feel like I can fix mine. Oh my god, I have to do like union find or something. I should have known this was like a union find type of thing. DFS plus heap. Okay, my problem is I cannot be doing this. This is way too, it's not very slow. I need to group them in like components. So let me see. I think mine's toast. It's too slow, so I need to write the code for stuff like I have to keep track of components of the graph. So we'll have here default default get list for UV in connections graph of u dot append v. Okay, that's basic. Then we need to create components here. Okay, I don't like this guy's solution. This guy's solution is weird. Is BFS. Give me BFS. I guess this one. I don't really like the union find. I mean, I guess I can. Okay, so we create the graph. I mean, yeah, that's what I did too. Okay, we do a union find here. And then union connected stations for A, B are to find A, find B. If they don't equal, then parent of RB is equal to RA. Link nodes in sorted order with each component. Process each component. This is kind of hard, bro. It's like another union find. DFS plus P. I guess I'll try it. So it's just, okay, we traverse every single node and basically okay, so we do this, right? Like it puts them all into different components. Components, and then component index, and then component index is less. If it's negative, then append a list. Okay, I get the idea. Let me try it myself. Okay, so the idea is component ID equals 0 for now. And then basically and then we'll do components. It's the list, okay? And we'll do while. So yeah, for every ID station, for every station in range of C plus 1 to 1 to C plus 1, right? I need to put it in the correct component. So we're going to say whatever station C gets me to, that's going to be in the same component. So we'll do components of components of so comp ID is oh well, there's nothing there, so I need to put something. Well, I don't even know how many components there are to be, so we need to append an empty list, right? Then components of comp ID is going to be that list. Append station, basically. And then whoever I source equals station while q equals dq with the source and q there. Q dot cur dot append Q dot append not append pop left comp we need to do okay yeah, this is just put this here. Comp ID, right? Not comp ID, what am I doing? Cur. And then for every x in graph of cur, x dot or q dot append x. Yeah. And then after you finish comp ID plus equals 1, and then print components. Let me see this. It's probably gonna break, to be honest. Why is this TLing? What the hell? What am I doing wrong? Oh my god. It's because it's like a circle. Okay, just don't add everything. Let's do scene if x in scene cur scene dot add cur. Okay. So we have 1, 2, 3, 4, 5. I need a global set. Yeah. I need a global set. In a way, this gonna be like that. 1, 2, 3, 4, 5. 2, 3, 4, 5. Brother, what? I have an idea. If station in scene, just skip. I should just have one component here. There it is. Okay, now this one, each grid is their own component, so there should be 1, 2, 3. Yeah, perfect. Okay, so we have our components. Okay, now what though? Okay, I identify them correctly, and then for every operation and station in queries, if op equals 1, pass, else, pass. Okay, so what do we do when it's op equals that? Well, then I should probably still have power. So we'll have trues times c, and then we just say power of station minus 1 equals false. Okay. If power of station minus 1, if that is the case, then res else. So if power station minus 1, res dot append station, else, then we need to do okay, first I need to heapify the components. Right? Is that the case? Because he heapifies and checks if they're if they're also valid. Yeah. Okay, I see. I should store also components index. Okay, store the component index as well. We'll do this. A component index. Okay, I do need to have a, I guess, -1 and then times. It's fine. I'll just have times c. I'll just adjust. I'll make my adjustments. So component index is just basically, no, I don't really like this. I'm just gonna do component, okay, index. Okay, I want station to in component. Just give me a dictionary, and then just do the station to comp station to comp comp ID, station to comp ID, not comp ID. We want the cur equaling to comp ID. Yeah. So station comp ID is equal to station, right? So comp ID to station to comp. Actually, he actually puts them. He actually pushes it as a heap. That's actually really nice. Heap push, right? That and the value itself. Very nice. Okay. So then the station ID. Okay, now I know what to do. So comp ID, station comp, station to comp, which is gonna be the station. Yeah, and from that I know which component list to pop. We'll do what I guess comp while comp and comp of, what does he do here? While comp, that's just the index. So IDX, the actual component list is components of IDX, and then while comp and power of components of IDX. Why does he do another index slice of 0? Oh, the first element. Okay, yeah. The first element minus 1 is equal to 0. Oh, for me it's is false basically. And while not so basically I want a falsy. So while comp, we will do heap pop of the component. Yes. So if comp res.append what? Wait, I'm getting confused here. Shit, I'm losing my mind. Okay. I already have the component index comp, right? I have the actual list itself, and I want the first item minus 1 because of the index difference. Then I pop the thing out. So now if you're a comp, if you have stuff in there, res.append if components of index I don't get this part. This doesn't make sense to me. Just add if comp, then res the append comp of 0, else res the append -1. That makes sense to me. So the station is mapped to that. I store the actual current and the comp ID, and then I add everybody else. If I've already seen you, I move you on. Components.append the actual list. And as I make you, I push you to, actually push you as a heap. And then station the comp ID for every X and that, for X and then comp ID. Power is just mapped to a singular station. I'm also checking if the power, so this gives me the station, what component that this station belongs to. Then I go to that and I get the list, and then the list will give me the sorted resulting. Oh shoot, hold on. I feel like this is gonna break. Oh wow, actually works. Wow, first try. Yeah, that's perfect. That's a long video. I'll see you guys tomorrow.